Good afternoon, everybody. So today we have, as usual, another industrial talk. So today is a pleasure to have here Carlo Togni. So he has a nice team here working with Rio Intent to do advanced static sign-off. So Carlo has done his undergrad at Federal University of Rio Grande do Sul in computer science. He also has done his master in University of Illinois in Urbana-Champaign, USA, with a Fulbright scholarship. He also worked with CEDA time ago, and also he worked with Mentor Graphics, and now he's in Brazil working, doing a very nice work, managing a team that is working in the tools for in the context of Rio Intent. So thank you very much, Carlo, to accept our invitation, and the floor is with you.
Okay, thank you, Professor Reis. It's a pleasure to be here. Thank you all who are watching today talk, and hope we'll have a nice opportunity to learn a little more. So we're gonna be talking about the work we do at Rio Intent and Saggi, and there are some interesting technical aspects to it. So I hope you will enjoy. So establishing our players here, why we do what we do, and who is it that we're doing, speaking a little bit more about us. So Rio Intent has been the leader, one of the leaders in advanced static sign-off for some time now, and the first 4 topics you see in my bullets here, they really are, they really come from the field. They really come from users using our tools, and that feedback has been really very well established for some time. So our tools do present a very good coverage in detecting the failures. Probably the second bullet is the topic where we have had the biggest lead in the market for the past years. Capacity and performance have been really a hallmark for our tools. Besides detecting the right failures, we've been developing technology that detects the lowest number of noise too. So and we also strive to support our customers the best way we can. So that leads to the last bullet, which is testimonials that are really, really awesome. So Rio Intent has been in this market for over 20 years. They're based in Sunnyvale in the Silicon Valley. It's not a very large company, but we have been experiencing steady growth for the last years, and we really have been reaching the big league for this last years, which is real nice. Saggi is a local company here in Porto Alegre, and we've been working with Rio Intent for over 10 years now. So that's really good. And we have a team of 5 people here in Porto Alegre, or close to that, not close to 5 people, not discounting anyone in the team, close to Porto Alegre. Actually, one of our guys ran away from Porto Alegre this recent days. Still in the who we are. I wanted to, before starting with the more technical part of the talk, I would like to introduce you to our product offerings. So we basically have 3 different families. Our Ascend family is the actual static verification. In there we have the very well-known Linting tool, which is an entry tool to verification, but it also an important entry-level starting point. Our autoformal tool is an implied intent tool. It uses the formal methods to perform structural verification, like coherence of your state machines, bus contentions, bus range and indexed bus ranges, validity of bus ranges in use conditions, and that type of situations. Then we move to the Meridian family, and this family is our flagship, right? This is where we have had the most market success, and then these are the most established tools we have. CDC is probably the main issue tackled in static sign-off. So our clock domain crossing tool has been in the lead for some time now, and that's why I picked this one for us to talk a little bit more on the technical side of things. Why is it important, and how do we tackle that? And CDC actually does spawn into different products and specific applications in itself, right? It sounds like a simple problem, but most of you are probably well aware that complexity doesn't stop increasing, and block levels and SOCs with, the number of blocks keeps getting bigger and all of that. And so those things really increase the complexity level and the need for new ways and new tools to verify those designs. So RDC is a reset domain crossing tool. It is analogous to CDC, but dealing with reset trees and reset scenarios and all situations with how the data that's been reset crosses to a different domain. It also has its specific challenges. Then the last product in the Meridian family is still in beta stage, and that's the RXV, which is a reset and X verification. X like the simulation, X value, undefined value that designs, digital designs, they can generate real undefined values in the real circuit, and there's verifications that we run for telling the designer what are the X sources they have in the design and how to correct them, and the reset tree itself, it can be optimized with that goal in mind of having an X-safe design, having not allowing X sources to propagate, and also detecting situations where you don't actually have to initialize a register, like if you're dealing with a FIFO or a shift register that you know they'll get to a set stage. You don't have to reset flux in those cases, and you can optimize your design in that way. So our last family is the VRIX family, and we also have a CDC offering in the advanced family, and in the specific CDC solution in the VRIX family is a multi-mode solution. So with dealing with power and different blocks and disabling and slipping off these blocks, clocks might be switched off, and you have different clocks being switched into line. So it's also becoming very complex for tools to deal with switching those clocks. So the CDC in the solution in the VRIX family, it allows for verifying all the modes and detecting all the modes that need to be verified independently in the circuit. DFT is also a new tool that is coming to our advanced tool family, and it's a design for construction, design by construction verification tool. And then the last product in our family is SimFix, which is also an X verification tool, but the SimFix, it allows you to apply corrections to your simulation files and running modes, so you will make the designer free of having to check for false, optimistic X's in the case where an X could be actually generated and the simulation didn't generate it, and pessimistic X's, right? Pessimistic where the simulation is generating an unknown value, undefined value, where it cannot actually happen in reality. So this is basically our offerings, and I think it's interesting to explore the CDC case a little bit further. So we're gonna jump into that and start looking into details of what happens in the CDC and what are the solutions and challenges there. So like I talked before, sometime I'm from the time actually where SOC sounded like a scare the developer type of example. We would use this argument, but not a big number of designs were actually SOCs or big SOCs. Well, today it is a very true reality, as you know. Most of the designs, complex, medium to complex designs, they all involve a large number of IP blocks with different specific functionalities, with clock domains, power domains, with it's really a nightmare in the complexity. We're jumping to, from hundreds of millions of gates to billions of gates design sizes, and it's really hard and next to impossible to tackle verification of that kind of complexity with just simulation and traditional techniques. It takes too many resources. It takes a lot of time to run the simulations, and it takes a lot of time to detect a violation. So it's really not practical in many cases. So we need other solutions for those cases. As an example here from our designs that we face in current user situations, you know, there are many designs with within numbers of like 100 different asynchronous clock domains in a single design, and thousands of tens of thousands of different signals crossing clock domains. So imagine if you have to verify by hand, manually verify if all those nets are crossing different domains safely. It's just too complex. Thinking of the design complexity, if we take the next step and propagate that reasoning to how do we actually verify all these clock domains, we'll have to start thinking. So how do I tell this tool? Okay, I have a tool that is able to identify clock domain crossings. How do I verify that? What do I need to tell this tool for it to run in a proper way? So I need to tell the tool what are the synchronous clocks, what are the derived clocks, what are the asynchronous clocks. Many of these clocks, they come from external sources. They're generated clocks, and there's just sheer huge number of signals and input nets, input signals that we have to define and set up so we can run this. So setup is complex. Is one of the challenges for using a CDC tool. Writing waivers for tool limitations is also a complex task. Running a manual check of crossings is next to impossible. Debugging is difficult, and if after all of that work I have a tool that generates a noisy report, and I'm also lost in the woods. I'm also without a sharp enough tool that I can peel my onion. So let's start defining things a little more, right? Let's remember the basis of our verification task here. Okay, so the most traditional and the most common way that a clock domain crossing affects our circuit is the metastability problem, right? When a signal moves from one clock domain to another clock domain, which is asynchronous, it can easily violate setup and hold time for the receiving domain, and that causes metastability. These situations, they are hard to detect. They can really propagate to the production chip and and corrupt signals in the production chip, and they are hard to detect in simulation. You need to add timing constraints to your simulation, and you have to run, a long set of clock relationship possibilities. So they're just, it's just a hard to detect problem. Thinking now of some of the logical effects, of the effects in the logic that the domain crossings can cause. One that's not even related to metastability is loss of data. If you are moving from a fast clock domain to a slow clock domain, you may easily lose data. You may easily lose capturing some particular data you were expecting to capture. So this is a restriction on your logic design. One of the other problems that might be caused is correlation in between different signal used in different circuits. If a signal crosses a clock domain and it fans out to different circuits, to different synchronizers, each synchronizer for this fan out, they could capture a different value for that signal. So it could cause logic difference in between the two situations. The next problem that we want to talk about is data corruption. Here's one thing that we didn't talk about before, just giving one step back. The classic solution for the metastability problem is a synchronizer, right? It's a simple solution and it works nicely. You just add one extra flop at the output of the flop at the frontier of the clock domains, and that will deal with metastability very nicely. But if you don't synchronize your receiving clock domain, if you don't have the proper synchronizers, then the metastability may really propagate down through the circuit and corrupt your data downstream. Same thing happens if you have logic in between different from signals in different clock domains, and you go to a third domain with the synchronized data. You may also cause a glitch in the original signal that may be transmitted and propagated through your circuit. So, and all this, still in this slide, I want to say to that, all these problems, they seem simple enough, but in a large circuit, in a large design, it's in a multi, in a large team designing a circuit, it's very common, very easy to commit mistakes like this. Because a designer cannot think by himself on all of the possible situations of how a net can cross a clock domain. inadvertently. So we need tools to enable them to verify those errors. So here's how we deal with these problems. Let me just skip to the next slide to see if I'm where I think I am. Okay. So this is a summary of the types of errors we talked about, and we need to be able to detect in our circuit the relationship among the clocks and how the data is being propagated among all those clock domains. So we need to find with our tool all kinds of glitch scenarios that could be caused with different circuits using, sometimes there are flops in the circuit that are used, they're not designed intentionally as for being a synchronizer, but they could end up working as a synchronizer and could mask errors. We need to detect reconversions of nets from that have crossed clock domains. We need to detect when synchronization is not done correctly, like in this first example to the right here. This structure looks like a synchronizer, but the clocks are actually inverted, so this is not a solution. We need to detect what kind of nets have fan out from a different domain, and that could cause the correlation issues. So each one of the single errors a designer can make, it can really diverge into the ways it manifests in the circuit. So and each situation then requires a different solution. So we did build a complex tool that's able to detect all those kinds of situations and able to help the user the most on how to fix those. So this is another general circuit here, and we're trying just to establish some of our terminology here. We call a data signal, a signal that crosses a domain and doesn't have a synchronizer. We call a control a signal that crosses a domain and does have a synchronizer. And we detect as a feedback path nets that are returning to a previous. So all of these categories, they help into building the more complex cases and helping the user in identifying exactly where is the error. So the error could be in the feedback loop. It could be in the where a data should have been synchronized. So we do need to build bigger and bigger cases for helping the user to detect complex situations in the design. Okay, a little further down here, speaking a little more into the complexity of the CDC issues. Like we said before, but just a little more but exemplified case here. When we have a fast to slow transfer of data, so this shows here what we said before. We can just lose the capturing of that data. If we have an improper data sequence, data enable sequence, in here we have both the data and the enable crossing a clock domain, but only the enable is being synchronized, then we can cause a violation because the data is not synchronized. When we have different signals being synchronized and they reconverge, we can cause a corruption in the value that's propagated, because the synchronizers captured a different stage of the data, and the data itself was mixed up. One bit was mixed up with the next one. So in our tool, I guess this is a little more of a commercial slide, but some of our claims that we do detect the most precise violations with all our technologies. Let me see. And yeah, I guess we're gonna skip this one. So in the we keep on building on the complexity of the verification and the cases we tackling, and then thinking again of complex designs. One of the things that help is to have the ability to run our verification hierarchically. So we can actually do that. We can run all the individual blocks apart, have our CDC checks done, fixed, and then we can feed all the data from the blocks that have been run for the integration check at the top hierarchical level. Again, as I said before, one of our performance and capacity have been one of our advantages over competition, and solutions like the hierarchical runs, they have been allowing us to keep that lead on. Here's just a couple examples of performance on different designs for a hierarchical run and a flat run. So in general, that's the justification for the CDC checks. Let's move on now with the reset design crossings, the reset verification. And like I said before, the reset domains crossing is analogous to clock domains crossing, but it presents its own challenges. So some of the principles and the challenges for the reset trees, they are, as we have metastability with the data, we also can have the reset deasserts causing a metastability. If the different clock domains are not properly synchronized, a reset change in the data can also cause a metastability in the receiving domain. Reset glitches can also be caused by soft resets and resets being generated, and the reset correlation problem is also possible. So like we did before, let's take a look at some of the examples of reset issues. So if we have a soft reset, we're calling a soft reset a generated reset, a reset that's derived from other nets. So in here, there's a convergence in the reset signals, and this convergence can cause a glitch in the reset signal, and this glitch can propagate to our circuit. So this is a potential of a glitch because of the reset logic itself. In the cases where we have a loop for a reset net, the reset can also cause a glitch because it will feedback and it will cause the net to not be settled. The traditional case, again, the most common and well-known case for domain crossing issues is the metastability problem. And here again, with complex reset trees, we can cause many of the reset signals across our design. They can they will be affected by logic, and they'll be synchronized somehow to different clock domains, and then these nets will propagate. They can propagate through the data path if the the flop that was reset is not synchronized at the destination, and by similarly, if the reset signal itself crosses a domain, it may also cause a metastability issue on the receiving flop. These two cases, they are particular because in one case, the reset issue is propagating as a data issue, and in the other case, the reset net itself is what causes the metastability in the receiving domain. So The correlation problem also has its analogous in the reset crossings, in the reset domain. And if a synchronizer happens on a fan out, and that synchronized NAT is used as a reset in another flop, then we need to report that reset signal may cause may have an inconsistent value because of correlation issues. So again, in our RDC solution, we also provide a hierarchical solution which allows for bigger capacity and for ensuring that RDCs that all the reset domain crossings are taken into account in all the situations, both at the block levels and at the integrated full design. And here's one example of a benchmark in between our runs, and I ran from our tool and I ran from a tool in a competition. And these numbers, they are very realistic. They are a good example of our technical capacity. The number of violations our tool reported is 1,000 times smaller than this other tool, and our runtime is a third of competition. So these numbers are really impressive, and these are a result of being able to really classify and detect the individual particular situations of violation in each design, in the design. So I guess we're heading towards the end here, and I think our last the last part of my talk here, I will talk about our multimode clock domain crossings tool. So RIG CDC is the advanced multimode CDC check for static sign-off, and and like we said before, I mean, when the most complex the designs get, the more relationships will there exist in between clocks. And this is one example of clocks being switched over into a circuit, and sometimes, some cases, if the user just blindly looks, if a verifier gets to this design and he looks that there are 3 different clocks here, and so the clocks can have there might be 8 different modes that we have to check this circuit for all the different clock combinations. But if we analyze this further, we can eliminate modes that cannot happen together, and really lower the number of runs needed, and the time taken into setting up and running all these modes. So it's if for a user to do this manually, the identifying of the clock modes, it's error prone, and it takes design knowledge, and many times the user will have to pick a few modes to run, and then it's not guaranteed that they will be able to get to the worst case modes, and important failures may be missed. So taking this simple circuit here, so there's 4 possible modes that can happen here, and I guess I talked about this already. So to enable the analysis of the different running modes, we can take in account what's been informed in the definition of the clocks and the environment files that define the clock relationships, and from then on, the multi-mode can run for all possible modes. It doesn't need to be set for specific modes, and it will enable or disable or run just the specific modes that are real and that are problematic, because it will know the clock relationship, so it will know when 2 different clocks are synchronous to one another, and those specific modes won't need to be run. Like I said before, since we're getting towards the end here, I wanted to show you an example of the look and feel for our debugging tool. This is the top part is a short portion of one of our results tables. And in here we are reporting the situation where a multi-clock crossing is possible. So there's a net that can have different clocks driving it, and there's a destination net which can also happen to have those, and so the user can analyze those 2 nets, and they can establish new constraints for those runs to disable some modes specifically, or to enable them. This is a way for the user to tell the tool to drive specific modes, and to add his design knowledge to the analysis. So in a multi-mode context, we can interpret and identify CDC issues, like I've been saying, when specific clocks have a known relationship, and if a specific mode, in this case, if the mode for both clocks is the same, is clock 1 here, and in this case, then everything is synchronous, and you don't need to run that mode. If you run that mode, you will not detect any violation for this nets, the nets in this situation. Again, all the specific and detailed clock domain checks are run into multi-mode, and they generate accurate reports that allow the user to debug the design. And I think that to finish here, I'd just like to add another benchmark table here. And if for a specific design there are 40 clocks, it would take 10 different runs in specific modes for a sign-off in single mode. And all of that is checked in a single multi-mode run. So that saves a lot of time, because the multi-mode run is only a fraction, takes a fraction more of time than each single mode run. So my slides here had more contents, but I guess my expectation was to cover what we did up to this point. So basically, I would be available for questions now if anybody has questions.
Well, thank you very much, Carlo. So if anybody has a question, please, it's the moment to do. I verified here in the chat, I asked the attendees, and if there is anybody that don't understand Portuguese, and there is no reply, so maybe as I think everybody understands Portuguese, maybe we can do questions and answers in Portuguese, no? Ok?
Sure.
Bom, então, switching to Portuguese, e que tiver alguma pergunta, por favor, coloque nesse momento no YouTube. Não sejam tímidos. Enquanto isso, uma primeira pergunta para o Carlo aí. De todas essas ferramentas da Real Intent aí, quais delas vocês estão trabalhando em Porto Alegre?
Então, na verdade, nós temos praticamente duas equipes aqui, né? A gente tem... nós somos 3 pessoas trabalhando em desenvolvimento e 2 pessoas trabalhando em verificação, né, em quality assurance. Os meninos que estão trabalhando em quality ali, que que são o Guilherme e o Thiago, eles estão trabalhando, acho que com o Lint e com o Autoformal, né? Na verdade, são ferramentas que a gente não chegou a falar em detalhe, mas eu não sei se eles estão por aí, eles podem até me corrigir se não for bem verdade isso, mas eu acho que é mais ou menos isso. E os outros três, né, estamos trabalhando em funcionalidade mais core, né? A gente está, na verdade, trabalhando com modelo do circuito, né? A gente usa, na verdade, dois modelos diferentes, assim, né, durante análise e debug, e a nossa equipe aqui tem trabalhado com o modelo de design para debug, que permite a visualização em esquemático das violações.
Ok. E tiver alguns dos assistentes aqui interessados em trabalhar contigo aí.
Temos oportunidades, tá? Meu e-mail está no meu último slide ali. Colocamos aonde no chat lá do YouTube. Eu não sei se está o meu e-mail por lá. Como é que vai ficar isso aqui, não sei.
Bom,
eu coloquei no chat do YouTube o meu e-mail lá. E sim, temos oportunidades. E a nossa filosofia de contratação é sempre pela qualidade. Então, estamos procurando, sempre temos, nosso CEO sempre diz, sempre temos oportunidade para pessoas capacitadas.
Ok, ótimo. Aqui o Guilherme Medeiros colocou no chat que...
Isso, confirmou lá que
ele trabalha com Linting e o Thiago com o Autoformal, né?
Isso.
Tem uma pergunta aqui do professor Paulo Mino. Para os PLLs, o sinal de clock utiliza os circuitos de recuperação de clock CRC. Também poderia ser utilizado dentro de um circuito integrado em diferentes estágios para também realizar esse sincronismo?
Vamos ver. Na verdade, assim, a parte funcional, ela não é o meu forte. O circuito de recuperação de clock, ele é um circuito de recuperação de sinal, de formatação de sinal, ou ele é um circuito de power control?
Palomino. Tu tens aí a cópia da pergunta também no Conf.
Eu liguei, entrei no YouTube também, eu estou acompanhando o chat ali também.
Então, o Palomino puder descer aí para o
estágios para realizar o sincronismo. É que o sincronismo em si, né, indo pelo que eu estou entendendo da pergunta aqui, né, o sincronismo perde a fase em comunicações digitais.
Sim, então o Palomino está dizendo sincronismo mesmo, ele perde a fase das comunicações digitais.
É que, na verdade, assim, né, o nosso approach, ele é verificação estática em nível lógico, né? A gente não está lidando com o sinal de clock propriamente dito, né? A gente está detectando possíveis violações, né, possíveis erros lógicos causados por problemas que são decorrentes da árvore de clock, né? Então, o que a gente chama de sincronizador dentro do CDC na verdade, aquele circuito digital ali com 2 flops em sequência. É isso que eu chamo de um sincronizador. O sinal de clock propriamente dito não tem nenhum tratamento. Na verdade, o que a gente indica para o usuário é que aquele sinal específico ele fez uma travessia entre dois domínios de clock e ele pode causar uma metastabilidade ou um erro de valor, enfim.
Okay. Mais perguntas, turma? Tem uma outra, em termos de interface com os frameworks aí tradicionais, como CADE, Synopsys, Mentor, tem alguma diferença para vocês ou não?
As nossas ferramentas, elas são mais point tools, assim, né? Elas não são normalmente integradas em termos de fluxo de projeto com outras ferramentas, né? A única... A execução, ela é basicamente standalone, assim, né? Ela roda independente. Os nossos arquivos de setup que a gente precisa, na verdade, né, eles são basicamente, a gente lê o arquivo SDC, né, mas afora isso, para rodar, por exemplo, o CDC, o usuário precisa definir um arquivo de configuração que determina todas as correlações entre os clocks, né? Toda a relação entre os sinais de clock. Então não existe um fluxo dentro do fluxo tradicional, né? Tirando depois o Synfix, né? Que é uma ferramenta que vai integrar com simulação. As outras ferramentas, elas são mais individuais mesmo.
Ok. Bom, então eu gostaria de agradecer ao Carlo aí pela ótima palestra. Dar meus parabéns aí, né, por fazer microeletrônica em Porto Alegre, né?
Obrigado, agradeço a oportunidade também.
Para nós de ver um pequeno ecossistema de microeletrônica em Porto Alegre, aí, né? A CEITEC, né, que tem um papel importantíssimo aí no setor, tem uma matemática ali no São Paulo, tem uma
verdade.
Agora, então, a Rio Intent, a Silvaco em Porto Alegre.
Isso.
E também tem a InPlace, que está sendo incubada ali no Instituto, né, com o Alcides e o André. Então, já é um cenário que tem sido, digamos, um orgulho para nós de ver que, do ponto de vista industrial, tem sido feito um trabalho aí muito interessante, né? Agora a gente vê toda essa discussão a propósito da CEITEC, né?
Estamos vivendo...
esperamos que isso aí seja revertido, né?
Sim.
Eu não sei se alguém assistiu, quem de vocês assistiu ontem a live aí, que foi ontem às 7 da noite ali com o Sérgio Bump, o ex-ministro Sérgio Rezende, o Omar Paranaíba, que é o atual coordenador da CECIDA SBC, e mais outros aí, não estou citando todos os nomes, mas uma questão importante ali que foi colocada até que a CEITEC foi criada por lei, né? Então só poderia ser modificada por lei, né? Isso é uma coisa que ainda tem pano para manga aí, esperamos. Não sei quem de vocês também já teve a oportunidade de ler o relatório lá da PPI, do Ministério da Economia, né, que é um documento de 200 páginas, com um conjunto grande, tiveram um trabalho grande para fazer um monte de copy-paste da internet, para mandar o dossiê, fazem vários elogios à CEITEC, mas aí terminam fazendo um trabalho de contador, né, só de fluxo de caixa da CEITEC, sem analisar o papel importante de todo o ecossistema de microeletrônica, né, que é estratégico para o desenvolvimento de um país, né, de poder transformar as ideias em produtos que não ficam dependentes só do exterior, né? Mas, bom, mas isso é outro pano para manga, né?
Não, é verdade, concordo e assim, agradeço a oportunidade também e realmente, né, a perspectiva de de contribuir com a nossa indústria aqui em Porto Alegre é algo muito motivador, assim, né? Nós temos tido essa oportunidade e esperamos poder continuar.
Então, quem quer trabalhar em CAD em Porto Alegre aí tem algumas possibilidades aí, tanto na Linting Saggi como na Silvaco, né? Esperamos que a InPlace lá também cresça e também tenha mais oportunidades, né? Então, podemos dizer que hoje um dos centros de DA no Brasil está aqui em Porto Alegre, né?
Uhum.
Temos também a CDC lá em Belo Horizonte, né?
Isso.
Também tem desenvolvido. Então, bom, alguns resultados positivos se tem aí de todo esse processo aí de formação de recursos humanos na área, né?
É verdade.
Então, mais uma vez, parabéns aí, Carlos. Foi uma ótima apresentação. Né? E esperamos que todos os que estão participando aqui dessa palestra retornem sexta-feira aí para assistir a palestra do Anton Domi, que é 1h30 da tarde. Né? O Anton Domi tem uma experiência enorme. Ele na CADE dirigia aí milhares de pessoas na área de ciência física, né? Então ele se aposentou lá, apesar de ser novo, se aposentou não faz muito tempo, né? E agora então está atuando junto a Stanford. Então, para quem gosta de entender melhor aí os problemas de atraso em chips, né? Ele vai fazer umas variações novas aí em cima do Elmore Delay, né? Que todo mundo conhece, né? Uma métrica tradicional aí de cálculo de atraso, né? De aproximação. Então, esperamos ver todos vocês aí de novo na sexta-feira e quarta-feira que vem. Então, temos mais uma palestra dessa série de Industrial Talks, né? E já temos palestras aí que estão agendadas aí até outubro já, né? Então, tentando montar um panorama que tem de empresas atuando em microeletrônica na América Latina, né? Seja empresas brasileiras, né? Ou empresas do exterior que estão atuando aqui, né?
Uhum.
Então, já temos confirmação, por exemplo, da Intel da Costa Rica também. Né? Então, o panorama em termos de empresas atuando é maior do que muitos poderiam esperar. Né? Então, Carlos, mais uma vez, obrigado aí. Deixa as tuas palavras finais aí.
Ok. Não, era isso. Acho que é isso mesmo, né? Temos para quem está interessado em oportunidades, aí temos oportunidades, sim. O ambiente é bom de trabalho, é interessante, né? Estamos lidando com tecnologia nova, com desenvolvimento de tecnologia, com casos reais, né? E é um momento bom para a tecnologia como um todo. E é uma alegria para a gente poder estar em contato com a URGS aí, né, que é a nossa casa, foi a nossa casa aí por um bom tempo.
Ok, Carlos, obrigado mais uma vez, esperamos nos ver em breve aí. Queria também agradecer aqui ao professor Rafael Brum, né, que é o nosso principal responsável aqui pela toda a gestão aqui do sistema de videoconferência e transmissão pelo YouTube, né, e vejo todos vocês aí, então, na sexta-feira, 1h30 da tarde, né, e bom final de noite aí para todos e até breve.
Boa noite.
Tchau, obrigado.